Well, we have a treat in store tonight. Jack Newton is perhaps the most in-demand speaker to amateur astronomers in North America. And I think, without question, he is the outstanding amateur astronomer now living in Canada. And you will see why when you see what he has to tell you and what he has to show you. I've known Jack for more than 20 years, and during that time, he's always been passionate, involved, I would say immersed in astrophotography. That's photography of celestial objects. And he is now at the cutting edge of this field. He's doing things that we couldn't have dreamed of years ago, that it just was not possible. Technology has overtaken any dreams that we had of achieving what Jack has achieved in recent years. 20 years ago, unimaginable. He's now exceeding the quality of the best telescopes in the world just a generation ago. The best professional telescopes with the best equipment, the world's top astronomers. It's both his skill and the advance in technology that has allowed this to happen. And you're going to be seeing the very cutting edge of this right now when he shows you what he has to show you. Jack's interest in celestial photography can be traced back to 1957. He photographed, as a teenager, at age of 14, Sputnik 1. So this gives you an idea of the lifelong passion and interest and zeal, and you'll see tremendous success that Jack has had with his chosen field. Another example of the level that Jack has achieved in astrophotography, when Halley's Comet was approaching the Earth in 1985, still very faint, he used his telescope to photograph the comet. He was the first to detect the comet from Canada. First person in the country to see it, to photograph it. And that image that he took was used to refine the trajectory of the European Space Agency Giotto probe that was on its way to Halley's Comet, along with images taken at 4 other professional observatories. And he is often called upon to do this kind of work to augment serious research projects. His observatory now has a number from the Smithsonian Astrophysical Observatory of professional observatories around the world where, when his observations are sent by electronic mail to the Clearing Center in Harvard, his observations are included in observations from mostly research observers around the world, research instruments, and combined with them to augment them. And in some cases, he has made the very first observations as similar to the one that I just mentioned. So we have a very distinguished and accomplished person to speak to us tonight, one that every amateur astronomer in the country knows, and only wishes that they were able to have the setup that he has, as you will see. So without any further words of interest, yeah, there is further words. I could go on for quite a long time, but there's a couple other things I'd like to mention. Jack is the recipient of the highest award of the Royal Astronomical Society of Canada, the Chant Medal, for outstanding achievements by amateur astronomers. He is the recipient of the Amateur Achievement Award of the Astronomical Society of the Pacific, which is a major American organization of professional and amateur astronomers, as is the Royal Astronomical Society of Canada. And that's their highest amateur award. His pictures have been published in hundreds of magazines and books, including my own. His have been used to illustrate articles that I have written myself, and I have selected his images as the best possible for some subjects to include in my books. So if this sounds like a superlative, a list of superlatives to describe Jack, there's no other way to do it. So will you join me in welcoming Jack Newton this evening? Thank you.
Gosh, after an introduction like that, my God, I'm going to have to be 110% tonight. I started astronomy, as Terry pointed out, when I was very young. About 12 years old, my parents had the foresight to see that I was interested in astronomy. They bought me a little 2-inch refractor for Christmas. It was called a Jupiter, I think. It was the princely sum of $21. Then that's worth $62,000 today. But it was a Christmas present that probably started the seeds of astronomy budding within me, because I spent countless evenings with that telescope looking at the sun and the moon, and I independently discovered Jupiter and Saturn as I watched the night sky each night as the skies progressed, and lo and behold, I couldn't believe my eyes when I hit Saturn with that telescope. A bright star was rising, and through that telescope on it, and could actually see the ring system. There was no books available for amateurs then that would tell you that you could see the ring around Saturn with a small telescope. All you had were these great photographs taken with the greatest observatories in the world, and one would think that, you know, us mortals would never be able to see things that those observatories and huge telescopes could see. And I would tell my school chums that, gosh, I can see Jupiter with belts and with Galilean satellites around it. And they'd say, sure, Jack. Totally disbelieving. And with that sort of put down, I felt, well, by God, I'm going to get a camera and start taking pictures, and I can rub it in their noses and show them what you can see through a telescope. So I was a paper boy at the time, and it was around Christmas time, and I was able to acquire enough tips from my paper route that I was able to buy the body of a single lens reflex camera. That's a camera that allows you to see right through the lens. I didn't have enough money to buy the lens because I really didn't care. I wanted to plug that camera into the telescope and take pictures. And that's basically where I started way back in 1958, and I just kept on building bigger and bigger instruments. If we can have can I turn the projector on from here or not? Okay, thanks, Terry. That's M51. I use this for focusing because it's the alpha and the omega. We'll get to that later. Starting out with astrophotography, one really must look at what we've been doing over the years using film. Film is still the most popular media for capturing images of the sky, and best to do that really, besides a camera and tripod, is to piggyback the camera or telephoto lens on top of a larger telescope, where you can use the larger telescope to guide the smaller lens. Usually when I go to a star party, or when you're at star parties or at friends with telescopes, go up to them and say, gee, well, you're observing, do you suppose I could just maybe attach my camera to your telescope and take a short exposure while you're looking at something else? And quite often you'll find people very, very receptive to you putting your camera on their telescopes, and you can start getting some really exciting images of the night sky. This is a piggyback shot of the zodiacal light. And you can see this band of light, which is in the plane of the Earth's orbit, which is dust and debris lit up by starlight. This is a very exciting shot, one would think that that might be a comet. Not so. This is the liquid oxygen being vented out of the S-4B rocket of Apollo 14 as it headed for the moon. And what was really exciting with Apollo 14, they had docking ring problems, and they couldn't get the command module to couple with the S-4B rocket to pull the lunar landing module out, and they had to go later and later into the mission as they attempted. And the pressure was building up of the unused oxygen, and so they vented it. And as soon as they vented it, that revealed their position in the sky, because we could spot this sunlit cloud of oxygen through a telescope. And by throwing the telescope into the middle of the cloud, we could actually see the command module in the S-4B rocket moving through space with the stars appearing to move behind them. And we watched them maneuver and retrieve the lunar landing module out of the end of the S-4B rocket. All of this 10,000 miles out into space as they were hurtling toward the moon. So there's no doubt in my mind they really went there. The Milky Way. This is a piggyback shot. Halley's comet is right there. This is just a regular camera lens and a 10-minute shot piggybacked on a little camera platform that I took to South America with me, and my wife carted all over the southern hemisphere. The Incas believed that the constellations were actually the dark lanes and rifts in the Milky Way, and this is actually the llama, and that's its head with its two eyes, and that's its body, and the legs coming down. And if I could have extended the photograph, there's another llama that is suckling on this one. And they really made sense, because most people have to be really bent to make a big bear out of the Big Dipper and so on. Whereas these are very clear, and you really get to see the objects that they perceived as animals. This is the coal sack, and it's probably a much of a duplication of what Terry Dickinson showed at your last month meeting of the Southern Hemisphere. This was when we were down in Peru chasing Halley, and the only difference is Terry's shots were taken from Las Campanas and what appears to be much better sky, or he had much better camera. Eta Carina, and of course Halley's comet. There's Halley going past Centaurus A, the radio galaxy, and this was again a 10-minute exposure, just piggybacked on a little platform and guided with a C90 telescope. And in 10 minutes, you get the plasma tail coming off the side and this huge fan dust tail. Total eclipses of the sun, piggybacked again. This is taken through a 450 millimeter telephoto lens and then enlarged and copied. The diamond ring, that first burst of sunlight after totality. The moon becomes an easy target as you find the fast films of today. You can put your camera onto a telescope, especially at a star party, and with 125th of a second or a 500th of a second, you can capture the lunar craters. Now, to move into astrophotography, or deep sky photography, you have to start looking now at plugging the camera right into the telescope and using other telescopes, such as this one on the side, to guide the main telescope. The reason you have to guide it, of course, is because the Earth's rotating and there's motors that are moving the telescope to follow the stars to counteract the Earth's rotation. There's still some very slight adjustment that has to be done with slow motion controls to keep those stars centered on the plate while you take a long exposure. This is the first telescope that I built, which was a 12.5 inch. There was a cardboard sonotube. There was barbell weights. The main shaft was from a locomotive axle. All of this stuff was sort of scrounged up in the junkyards and put together as a telescope. Frank Shin, the planetarium director in Winnipeg, helped me grind and polish the mirror. And when I say help me, he did 90% of the work and I watched. But I did learn. The first observatory I built in Winnipeg, there was a 10-foot dome, and as you can see, as these things started to creep up into, do you have problems with these things? They creeping up. We've recently got a solution in Victoria. There's no street lights within a quarter of a mile of my home. Guiding the telescope, and this becomes much more difficult as you get larger and larger focal length, or more and more powerful telescopes. And so I designed a photographic platform. This is just a flat plate that will rotate, and besides this we have a Barlow lens to give me more power, and on the other side of it you can see that there's a set of prisms, and these prisms will rotate and the plate will rotate, which means I can pick up a guide star to follow almost anywhere in the entire field, which means I can probably have a choice of 15 or 20 guide stars for every object that I want to photograph. The reason for this too, this off-axis guiding, is that if the primary mirror of the telescope down at this end decides to move during the exposure, or there's a bit of flexure or sag in the metal, I will see it at the same time that the film sees it, because it's a star that's located just off the edge of the field. Here's the next telescope that I built, which is a 16-inch telescope. The tube was rolled by a shipyard and charged to an icebreaker. The camera's up at this end, and the main mount that I had built has just been modified slightly and enlarged to handle the bigger telescope. Now, to get better photographs through the telescope, one of the methods is to chill the film down to near dry ice temperatures, and by doing that you eliminate one of the great problems with film, and that's called the reciprocity failure of film. And just to make it very simple, when you first take a picture with film, it is very fast, say, and in 1 second you get a certain density. In 2 seconds you should get double the density, but you don't. And by the time you take 4 seconds or 8 seconds, the film now has failed so badly that it takes maybe an hour to double the density again. And that is called reciprocity failure. But by building a cold camera and applying dry ice to it, you can chill the film down to probably 50 or 60 below zero. Dry ice temperature is minus 109. And so the camera gets down to 60 or 70 below zero. And the big problem with that, of course, is that when you chill something down to 60 below zero, it instantly frosts over from the moisture in the air. So to get around this, you build a cold camera. And this is just a simple camera that you can see the film goes from one cassette to another. And there's a simple shutter to open and close. And there's an optical plug that pushes up against the film. This optical plug is a 2-inch block of plexiglass. And that keeps moisture from forming on the film. And because plastic is such a good insulator, you find that over an hour before the plastic plug even thinks about frosting over at the other end. And to give you an example, this is the core of M31, the Andromeda Galaxy. And this is a 14-minute exposure at room temperature or ambient temperature outside. And there's a 14-minute exposure in the cold camera. So you can see the dramatic difference that the chilling the film makes to astrophotography. This is using a large format cold camera, and you can see that it's a big circle. And that's the Orion Nebula, and that picture is 20 minutes in duration with the cold camera. This was taken with the old VR1000 film, which when exposed properly wasn't nearly as grainy as the first reports on this film. This is the Trifid Nebula, and it was taken with a C-14 at f7 at the Texas Star Party. I always look in the field when I arrive and find the biggest telescope and immediately make friends with the operator. Omega Centauri. This was a 12-minute photograph at f7 with a C-14. Centaurus A, also 14 minutes. Now, after you've taken most of the Messier objects with the new 16-inch telescope, it's time to move on to a 20-inch telescope. So I was fortunate enough to pick up optics in Riverside, or at least the blank, and talk my neighbor Leo Vanderbilt into helping me grind and polish it. And we built a new telescope. This one has a rotating top and sort of a strut design that had piano wire crossed in between each one for stability, and the tube is made out of steel, also at a shipyard. Now, one of the problems, of course, with photography, now that you've raised it up onto a trailer, is the height of the tube becomes nearly 10 feet. And that always creates new divots in the driveway. But with the 20-inch telescope, you now really start to resolve stars and pick up much more nebulosity in the same 20 or 30-minute exposures with the cold camera. This is the Lagoon Nebula. This is taken with Ektachrome 400, and it's a 30-minute shot with the 20-inch at f5. There's M33 taken through a light pollution filter, and you can see that at all the H2 regions, these little red are sort of the Orion Nebula-sized nebulae in this particular galaxy. It looks like it's got the measles. Now, my next telescope, having again taken most of the Messier objects with the 20-inch, was to move to a 25-inch. And this particular telescope doesn't have homemade optics. The mirrors were done by Galaxy Optics in Colorado. It's a thin mirror, 2-inch, f5. The new mount was built for it. There's 450 pounds of counterweight. The tube was rolled in 3 sections and welded. It has since been painted black to stop the thermal radiation, or at least to improve the thermal radiation from the tube, which made a dramatic difference in the performance of the telescope. And this is my dog Heidi. This particular galaxy, M81, has a supernova in it right now. I'll show you the supernova later. But this is a 20-minute shot taken with the 25-inch. M99 in the Virgo cluster. 20-minute shot with a cold camera. You can start now to see reddening in the core and blue arms of the younger generation stars. 65 and 66, I believe. Again, you can see the outer arms, the bluer younger stars. the North America Nebula, and this is sort of the Gulf of Mexico portion and south or toward Middle America or Central America. This is taken through a light pollution filter. It's a 20-minute exposure, and it's taken on VR1000, or sorry, it's taken on 3200 Konica in the 120 format. The Omega Nebula, this is a 30-minute exposure on Ektachrome 400 with the cold camera, large format, done in super slide. That's the 35 millimeter slides that take the blank part of the plastic and they open it up for the negative and the transparency. This is Zeta Orionis in Orion, and the Flame Nebula, or the Christmas Tree Nebula. This is a nebula that is just underneath the Orion. Orion is up at the top, and this is quite often overlooked. It's a beautiful both reflection and emission nebulae. It's you can see the pink of the emission and the blue of the dust reflecting the starlight. Orion in the 25-inch. This was my first light photograph taken with the 25. These were all taken from Victoria. Now, moving into another form of sensitizing film, and that's gas hyperization, and that's by taking this is hydrogen, and I'm pumping hydrogen into a container that I've made out of plumbing pipe, and you put 10 pounds of hydrogen into the tank with the film, and then I usually go to work and phone Alice and tell her to put it in the oven and bake it for about 4 hours at 125 degrees. This is not recommended for amateurs. However, it does make the film really jump. Hydrogen's a lot easier to handle than they say. It's about the same as propane, but it's a little more flammable. You can buy forming gas, which is a safer mixture, which is carbon dioxide and a little bit of hydrogen in it, I think about 7%, and that does the same thing, but it just takes several months. I'm kidding, a few more hours. This is the Eskimo Nebula, and this was taken on gas hypered 2415 or Kodak Tech Pan, and then it was dodged on the floor of my darkroom to get it large enough so that you could see some of the detail of the face that a lot of people see in one of Burnham's books that was taken by the 200-inch photograph. Now, every once in a while, you get crazy as an amateur, as I did, and I wrote an observing program for the University of Hawaii's 24-inch telescope, and to my delight as a Canadian, it was accepted, and I was given time by the United States on this instrument, and this is a picture of the 24-inch observatory on top of Mauna Kea. And this was my cold camera mounted on a custom designed backplate for the Bowler and Chivens telescope. I was going to do a 3-night run with the telescope, testing out the cold camera with the good skies of Mauna Kea. Unfortunately, a blizzard moved in, and we skied all weekend instead of observed. And as my wife was down lying in the beach and running the numbers off my charge card in many of the shops that were down along the beach, I was freezing my tush on top of the mountain pretending that I was having fun. However, it was a great honor to have the opportunity to visit the astronomers, see all the instrumentation, and be accepted as an amateur on an American telescope. The next project after the 25-inch trailer was the new Newton Observatory on top of Mount Matheson. This is the bottom of the pier being poured and filled with cement, and you can see the reinforcing rod in it. And this is mounted on a very wide, thick footing on bedrock beneath the sand, which would form the bottom of the concrete floor of the first level of the house. The dome had to be built within 30 days after work and on weekends because the crane that was going to lift it into position was arriving at that time to move the roof trusses to the roof. And so the dome was designed out of laminated plywood rings, glued and screwed together. This is half-inch plywood, 3 layers thick. Same with the arches that went over the top. And all the side support was actually those cedar lathing that you buy for the garden to stake up your tomatoes. And I bent them using the main rings here to bend them. Every night I'd bend a whole bunch more and glue them and screw them, and then they were eventually bracketed and screwed into position. The outside of it was covered with door skin, that thin material that is on the outside shell of doors. It's mahogany. And this was nailed on and glued on at the same time and bent into position. And then the dome was covered with fiberglass like a boat, 2 layers, and the fiberglass cloth to seal it up. This is the dome when it was put together and assembled at the observing site. And this is the crane in pouring rain, as usual, lifting the dome into position. And this is the observatory today with the sleeping quarters. And we've had, it's been in operation now for just about 2 years, and we've had just over 300 people through it. This is the back view. The house is a little deceiving. I built a theater in it, and it's all designed with my office underneath, which has also dual telescope controls for it, and then a machine shop for repairing and building parts for the telescope. Alice and I sat down one weekend and just designed our dream house and sketched it out and then turned it over to an architect to legalize. And I really recommend you do that because we didn't care about the resale value. All we cared about was designing a house that was totally functional for what we wanted. This is the observatory. The pier shrinks down beneath the floor from 36 inches square down to 14 inches so that the telescope can swing by it. You can see the tube is painted black now, and there's a CCD image on the computer screen. This was actually the first prototype ST6 that SBIG had. They sent it to me to do some testing and get some photographs with it, and it only had a very short cord, and so I had to have the telescope up about 7 feet in the air so that the cord would reach the computer to the CCD head. It was great fun. This is a more recent shot now with my new 386-33, which I use for 386-40, which I use for pulling the images from the CCD camera up here onto the computer and the computer monitor. This is the Santa Barbara Instruments ST6. You can see by the back plate, and there's some sliding color filters that are mounted in front of it. It's too big for my original off-axis guide tube, so we moved a guide tube to the side of it and adapted it. And it's nice to have a machine shop. This is the filter wheel with an eyepiece. In one position of the filter wheel has a diagonal mirror which allows you to take the light up through a crosshair to center the object before it hits the small CCD chip. This is a muffin fan just to draw heat off the heat sink, because the camera runs at about -40 below zero. Now this was one of the first test shots I did with with one of the prototype cameras, and it was at the Winter Star Party in Florida, and I used a Starfire 6-inch refractor, and that was a 10-minute exposure with the CCD camera. There's the colliding galaxies in the Virgo cluster. This was also a 10-minute exposure, and I think they're called the Siamese twins.
The same telescope?
This was now taken with the 25. There's, it's hard to recognize it because there's so much nebulosity, but that's the face-on galaxy M100 in the Virgo cluster. That's a 10-minute shot, and it's beyond 21st magnitude. There's Seyfert's sextet. That's a 5-minute exposure. There's what 20 seconds does. The Ring Nebula. There's 20 seconds of M82. "20 seconds of the face on the Eskimo." This is taken actually with the ST4. Now this was one that I didn't have a flat field for, but you can see this little line here. That's the quasar 3C273, and that's the 21st magnitude jet coming out of it. That is a 10-minute exposure. However, I can do a better job in 5 minutes. This was Pluto last year. This is a 20-second exposure, and you'll see that it's moved over. It was on top of this star. We were hoping for an occultation, but it missed, and the next night it moved over to here. I can back it up if you want to see the comparison. There it is, where it is there, and then it moves over one. I guess it moves toward me. This is what the computer screen looks like for controlling the camera. It's very user-friendly. You can select camera or display or some utility functions to control the image. This is showing a 5-second exposure, and you press enter, and this is what your exposure looks like when it's raw. This is what it comes off the telescope. It really looks pretty noisy. There's a lot of electronic noise in the CCD which you have to remove. And what you do is you take a dark frame, which is a frame of equal duration to the exposure. In other words, if you're taking a 5-minute exposure, then you take a 5-minute dark frame and save it. And then you take the dark frame, subtract it off, and there's the object. And the reason you do that is that there's electronic noise that builds up in the camera during the exposure, and you want to register that noise so that you can subtract it off of the image. And there's the bubble nebula. Now, you can also flat field your telescope. Because the light coming into your telescope doesn't hit equally all over. When you take an exposure of blank sky, this is daylight sky now, or at twilight, you can see how uneven the illumination is on the chip. And so you record that, and then that's divided into the image to flatten the field out so that you end up with a perfectly flat object. This is a series of Swift-Tuttle that I photographed and were processed by Richard Berry using different processes. This is a linear stretch where you change all of the numbers linearly, a gamma stretch, and this is his HEQU stretch, and then a rank stretch. And you can see the structure of the inner jets of the comet. And this is all done by manipulating the numbers. There's one that of Swift-Tuttle, similar to what was just published this month in Sky and Telescope. It looks like a butterfly, and actually these are main jets that are off of it, and you can see the dust tail. And the reason there's dots here, this was made up of about 12 10-second photographs, all superimposed on one another, and the comet's moving, so the stars end up trailing. Unguided, 10 seconds, and you just co-add them. There it is in false color. At least another night of shooting. I got over 50 photographs of Swift-Tuttle, many of them that were measured in astrometry and sent into Cambridge. You can see the actual geysers or jets coming off of the nucleus. The nucleus is actually bright white, and it's so bright that it caused what they call flip over and appears as a dark core. Now, balancing a camera, what you've got to do when you go into color astrophotography with a CCD is to select filters that will actually give you an actual rendition of what the night sky is. And the standard Rattan filters that we've used as benchmarks for tricolor photography for film over the years are not particularly good for astrophotography. One of the brightest lines of the spectrum is what they call double ionized oxygen, and it's at 500.7 nanometers, and it falls right in between the green and the blue layer of the Rattan filters. So that if you were to take a photograph of, say, the Dumbbell Nebula, you would miss this bright oxygen line, and so you would end up with the nebula being either blue or quite likely red because it's missing this big strong line of emission. And so you pick filters out that will give you a bigger overlap in the oxygen 3 range, and this will allow you to capture that line and more accurately give you a rendition of what the object would look like. There's also a problem with the blue and the green filter in that in a CCD camera is very, very sensitive to the near infrared, and so from here on out in the spectrum, these filters open wide open and allow light to go through from the CCD camera or into the CCD camera in both the blue and the green. And so you must get an infrared blocking filter to block the blue and the green so that this infrared doesn't leak through. And this is an example here showing the amount of opening up of the green here and the blue here. Everything past there is wide open to the red. Now here's some of the filters that I first started using in my tricolor work, and you can see that they're just mounted into plastic and they're slid into a holder, and I think we're going to need the next tray. Can I trouble you, Terry, to... And this laser is very good if anybody dozes off and I catch them sleeping. It's okay, there's only 80 more slides, you're all right. Now to color balance the camera, what I did was I put this photograph, which is a test photograph for a color lab, in my garage and hooked the CCD camera to my C8 and pointed the C8 at this snapshot. You can see a bit of red tape up at the top that it was hanging on the garage door with. And this is the standard gray card, which reflects the same amount of all wavelengths of light. And so I kept changing the exposure of the red, blue, and the green until I got the pixel density equal in all three colors. And just to prove it then, I took the exposure of this, put it onto the screen, and matched it with the photograph, and it was identical. So I now had the camera color balanced using the three filters to what your eye would perceive with sunlight from our star. That's about as far as you can say about color, because color is different for different wavelengths of light. So now you have to take three pictures. To do a tricolor photograph with a black and white camera, you must take a red picture, a blue picture, and a green picture, and then combine it in the computer. And there's the dumbbell. And notice how green the dumbbell is? And that's because this is the double ionized oxygen. And this is what the dumbbell really looks like. Most books show this as blue and misses that line. There's a shot that's the closest I ever took with it, and this was on VR1000, and you can see the green. It was getting some of the green anyway. It was more predominantly red. I think we've got some other examples. Here's a good one. This is a Ektachrome 400 cold camera shot of the owl, which was actually one of my favorite shots. That's what it should look like. It's actually blue-green. This is a CCD image that I took this year with the ST6. And this is equal to about a 10-minute exposure. The previous shot was a 30-minute exposure taken with the cold camera. Now, image processing, because the CCD image is merely 90,000 pixels, in my particular case, that each one has a numerical value of the light that has fallen on it, you can manipulate them, as I showed you in Richard Berry's sequence, using different things. This one is a Canadian program developed by Ajay Seagull, or Seagull Corporation, and some co-conspirators, which is called Hidden Image. And what this particular program does is very similar to how they corrected the mirror on the Space Telescope. And they take, this is a conventional photograph of mine taken in fairly poor seeing of M51. Then you do a point spread function around a star, and you convolute that star down to where it would be if it was diffraction limited. And that's the same photograph processed in maximum entropy, and you can see the enormous difference in detail. In fact, after processing with this particular, there's the full frame of M51, that compares very favorably to what the 100-inch Mount Wilson was taking in 3-hour photographs 10 years ago, 20 years ago. It's probably the biggest revolution that amateur astronomy has ever had. NGC 4449, an irregular galaxy. The only way to really appreciate what the CCD is capable of doing is to compare them with photographs taken by observatories. Here's the rat tail galaxies, two colliding galaxies with their nuclei intermingled. This is, I believe, M61, face-on in the Virgo cluster. Again, you can see the reddened center and the blue younger spiral arms. Here's M100 again. These are done in maximum entropy, and they're taken this year with the ST6 and the 25-inch telescope. The Crab Nebula. There's the pulsar, spinning 30 times a second, the remnant of a supernova. M99 in the Virgo cluster. This is M63, I believe, in the Virgo cluster, and you can see the dust lanes and the detail that's That's a little better focused. Again, I could never hope of doing this with film. M88. Virgo cluster. Now this is an interesting shot. This galaxy, you can see, has very unusual dust lanes, but what's more unusual is this red, green, and if you could see actually blue star. And what happens when you take red, blue, and green images one after the other and something's moving in the plate, you end up taking a red, green, and blue image. And that's an asteroid that I discovered, and this was about 2 weeks ago, and the asteroid is called Bitstrip, and it was discovered in 1978, and that is 18th magnitude. And because, again, it's a CCD image, this image is given to the University of Victoria. They take the 3 stars and position them in the computer. They do astrometry on the asteroid, and that's sent off to Smithsonian. The other thing that was interesting was I didn't know its position because I didn't have star charts readily available to give me the accuracy, and so I knew how far it had moved from the red exposure to the blue exposure because there's headers on each CCD image which tells you the time and the exposure length, and I extrapolated backwards until it was beside the nucleus of this galaxy, phoned that into the University of Victoria. Jeremy Tatum was at home at the time. He's logged into the computer. He brought up the asteroids at that particular moment in time, and bingo, that was within 5 arc seconds. So it's incredible what you can do with a CCD camera. M98, I think, in the Virgo cluster. NGC 520, interacting galaxies, again with embracing themselves. Edge on. Irregular in Virgo. This is a shot of, I think, M13. No, that was M92 and M13. The Black Eye Nebula. This is 2903 off the question mark of Leo. This is a 30-minute shot taken with the cold camera. There's 10 minutes with the CCD. There's a shot that Tony Hallis did for me in his lab at 300 dots per inch when he put it into the CD-ROM system and produced the slide. This is the galaxy that's in the bowl of the Big Dipper, next to the owl. M109 in the Dipper. Beautiful S spiral galaxy. Here's the again the full format of the cold camera, taking the Eagle Nebula with the Eagle in the middle, and there's the Eagle taken with the CCD in 10 minutes. (4565). The Bubble Nebula. Planetaries, again, this ionized oxygen, the line that's picked up, most of the planetaries appear blue-green. This is the supernova remnant Cas A, which was just a radio source until Sidney Vandenberg used the 200-inch telescope to trace down an unseen object and produce this with a deep shot with the 200-inch. This is a 10-minute shot with the 25. Edge-on Galaxy and Pegasus. The Veil. Some objects are very hard to improve on. You've got to realize that film is huge in its size and can capture an enormous amount of detail, and the CCD camera really has trouble. This is about the best I could do with a hunk of the Veil, and you can only take such a small segment of it. Galaxy and Virgo. This is M99. That is M100. 891 Edge-on Galaxy, and you can see the red and dust lane. The Horsehead. This is another one that's really tough to improve on from film. Intrinsically, it's just a gorgeous object. That's a 10-minute shot with a CCD. This is a little nebula just above the belt of Orion. It's both, I guess, a nebulae. It's got some emission in it and some blue in it, picked up in a 10-minute shot. This is a telephoto shot taken piggybacked on the telescope with a CCD camera of the Orion Nebula. And of course, a shot taken with the cold camera as a comparison. All I can take is the trapezium, the little cluster of stars in the middle, because the chip is so small. This is Hubble's Variable Nebula, and this is only a 20 and 30-second exposure. And this is M43, or the tuft that comes off of the Orion Nebula. There it is, done by Tony Hallis from one of my photos. NGC 4490, this was a star that had or a galaxy that had a supernova in it that I got the pre-discovery of some years ago, so it's a favorite of mine. There's a shot done on CD-ROM. Another shot of the Eskimo Nebula. The Bear Claw. M82. This is the jet coming out of M87. And you can see that it's blue. The Ring Nebula. This is a comparison now of M81, and watch the next photograph and the spot between the red star and this star in the triangle. There's the supernova. This was discovered a few months ago, and I guess is fading now slightly, but it's an easy telescope object. Comet Shoemaker-Levy, 1993E, I believe, and this is the one that was disrupted by Jupiter, was torn apart into pieces, and is coming in like a string of pearls. The debris along here is probably dust in the orbit. This is the tail coming off from the solar wind. I've got just a few shots of planets to show you. This is Mars, taken this year from my observatory and rather poor seeing. Saturn. I don't know if I can sharpen that or not. Maybe a little. Jupiter. These were all about 0.2 of a second. There's one of Parker's to compare. Don Parker taking using a Lynx camera and the 16-inch telescope in Coral Gables, Florida. Terry's just brought us a shot that'll blow these away, taken on the, I guess, just a few weeks ago in Chile with the Helen Hogg telescope. Some of Parker's Mars shots, these are actually well documented in Astronomy magazine. Parker's Saturn shots. And that's what happened when I got Parker's shot in photostyler and sent it back to him and told him that his optics were terribly out of alignment. And that's my last slide.